Is a new planet in the solar system about to form? There are hints that Planet 9, a supposed hidden giant, may be more than fiction, according to NASA's sophisticated AI computer. This algorithm identified faint light patterns and perplexing gravitational shifts at the extreme boundaries of the solar system while sorting through data from James Webb satellite telescope. There is a lot of excitement and skepticism in the scientific community. Is this the long-awaited smoking gun that definitively proves the existence of Planet 9? Planet 9's mystery. Astronomers have been debating whether Planet 9, a mysterious world in the solar system's farthest regions, circled our sun for a long time. When scientists discovered that several frozen bodies on the Kyper belt exhibit odd orbital grouping that is inexplicable by conventional theories, they started to speculate. The alignment of several of these far-off objects points to a gravitational pull from something far larger than any dwarf planet that orbits well outside of Neptune's orbit. New mathematical models were developed as a result of early attempts to explain these patterns, each suggesting the presence of a massive object that could be 5 to 10 times the mass of Earth. Given its great distance from the Sun, many observers assumed that if such a planet existed, it would be too faint to spot with standard equipment. There was little chance that its position could be easily revealed by the dim sunlight it would reflect. The concept of a hidden planet attracted significant attention in spite of these obstacles. Around the world, observers joined the quest, occasionally scouring the night sky for the smallest indication of motion against the starry sky. In addition to honing their thoughts about how the gravity of such a planet may group the orbits of frozen objects, researchers conjectured about the nature of this invisible giant, including whether it formed alongside the known planets or drifted in from somewhere else. Because it fit data sets more neatly than alternative explanations, the Planet 9 theory gained popularity throughout time. Other concepts were several smaller masses or random patterns. However, those hypotheses hardly ever agreed with the reliable orbital data. Even skeptics acknowledged that these strange alignments were the result of something. Determining the source and extent of the impact became the main focus of the discussion, rather than whether it existed at all. As technology developed, scientists looked forward to new telescopes that could more thoroughly examine the solar system's periphery. Others looked to space observatories, while others attempted to detect faint objects using powerful ground-based arrays. However, progress was sluggish, and the facts frequently turned out to be too dispersed or lacking to put an end to the discussion. Though definitive evidence was still scarce, discussions about Planet 9 persisted. The James Webb Space Telescope, JWST, followed, which has sensors designed to collect infrared radiation from the far-off cosmos. JWST's capabilities make it an attractive instrument to explore the outer solar system, even if its primary purpose was to study dim galaxies and exoplanets. It provided a new way to detect a single planet that might still shine dimly from its own heat, or reflect enough infrared light for sensitive detectors to detect it by gathering vast volumes of data in infrared wavelengths. These advancements prepared the way for a significant advance in our understanding. Instead of just optical images, astronomers suddenly have access to a multitude of high-quality observations. How to efficiently mine these massive datasets, filter out background noise, and eventually see what might be out there became the actual question. Planet 9 had evolved from a theoretical concept to a real target for cutting-edge technology. The James Webb Telescope's function. The James Webb Space Telescope, or JWST, provided something fresh to the search for Planet 9, which started with more traditional telescopes on Earth and in space, sophisticated infrared equipment that can pick up subtle heat signals at amazing distances. JWST's primary goal at first was to look back in time to see old galaxies and investigate exoplanets circling distant stars. However, its sophisticated sensors proved out to be equally as essential for investigating the edges of our solar system. When a telescope operates in the infrared spectrum, it might pick up signals that get lost in visible light photographs. Compared to shorter wavelengths, infrared radiation is more reliably emitted or reflected by very distant cosmic objects, particularly those orbiting in the frigid outer regions. In addition to revealing galaxies billions of light years distant, JWST's deep field observations also gathered a wealth of information about the dispersed icy bodies outside of Neptune. As it scanned these areas, it picked up innumerable light spots that were almost perceptible to conventional optical scans. Crucially, JWST's meticulous calibration and extended observation periods made it possible to get incredibly detailed images of these far-flung regions, including the Kyper belt. The stability and sensitivity of this telescope are among its best features. JWST circumvents many of the interferences that beset ground-based observatories by orbiting near the second Lagrange point, L2, which is far beyond Earth's shadow. Because of this, it can take repeated pictures of the same area with far less atmospheric distortion or stray light from our planet. These repeated observations produced an image archive that allowed for the detection of even minute variations in position or brightness over the course of days or weeks. In order to find heat signals from something big yet dim, astronomers could use sophisticated space telescopes that look beyond the visible spectrum, something that might only appear in visible wavelengths as a slight blur. Such an object may be noticeable in the infrared spectrum if it were Planet 9, particularly if it emits residual heat from its development or from modest radioactive decay inside. However, the enormous volume of data produced by JWST presented its own challenge. Innovative methods were needed to go through the numerous terabytes of spectroscopic data and pictures in order to identify a single weak signal, if one existed at all. In addition to direct light from potential planets, researchers also had to account for faint gravitational effects that could show up in many frames. A hidden mass might be suggested by minute changes in the motion of other Kuiper belt objects or by small distortions in the star fields in the background. I am a game share, Quantum A. The ability of quantum computing to perform tasks that are beyond the capabilities of conventional computers has attracted a lot of interest. When modified for artificial intelligence, quantum systems may analyze enormous amounts of data with the help of entanglement and superposition, which enable them to investigate complicated possibilities more quickly than a typical machine. In the process of verifying Planet 9, this highly developed technique proved to be invaluable. A quantum artificial intelligence, AI, may evaluate probability over a wider variety of characteristics simultaneously. Unlike a traditional computer that might search through telescopic images using simple filtering algorithms, comparing brightness, position shifts, or known items. It does more than just examine one picture at a time. Patterns that appear across several datasets can be mapped by it. When searching for something that only leaves tiny traces, like an unknown planet, this ability to see connections that could be imperceptible to everyday routines becomes more crucial. It was not enough for the new technology to analyze individual light particles in random frames. It examined the motion of objects within the Kuiper belt over time, looking for irregularities in their orbits that did not match known gravitational effects. The quantum AI was intended to identify the potential source of any external force, pulling on those far-off frozen bodies. The strategy is essentially the same as the one that helped astronomers discover Neptune in the 19th century by studying Uranus' motion, but it has been scaled up with sophisticated quantum-level computation. The AI analyzed gigabytes of JWST data, including deep field scans, repeated observations, and a variety of spectroscopic readings over the course of 72 rigorous hours of continuous processing. It methodically ruled out regions that might be known objects like dwarf planets, background artifacts, or small cosmic rays. By doing this, it detected a dim pattern in the infrared that coincided with a recurrent area where something seemed to have a clear gravitational pull. The note that the system composed was brief, yet powerful. Verify the anomaly. An object candidate was found. Data that, when put together, strongly suggested a slow-moving object with a constant gravitational footprint supported this claim. Additionally, the device recorded temperature data that were hardly perceptible to less sophisticated techniques. Stunned and interested, researchers realized they might be witnessing the strongest indication yet of an unexplored gigantic globe. The quantum AI's probability-based methodology provided a very convincing trail, even if it fell short of offering a direct snapshot. It narrowed the range of possible locations for Planet 9 or something similar by focusing on a limited region of the sky and examining the discrepancy between predicted and observed orbital speeds. This innovation, which was made possible by sophisticated technology and specific algorithms, is significant for the field of astronomy. An actual example of how state-of-the-art computing may extract important hints from massive cosmic datasets. Theoretical forecasts coincide. For a long time, astronomers have conjectured about the possibility of Planet 9, expanding on close examinations of trans-Neptunian objects with oddly grouped orbits. The dominant theory has been that these smaller bodies must be shepherded by a massive, invisible planet that is many times as massive as Earth. This would keep them in coordinated orbits, rather than allowing them to disperse haphazardly around the outer solar system. System. After doing a lot of calculations, scientists came to the conclusion that this invisible planet would most likely travel an elongated route, which means it occasionally goes quite far from the Sun before swooping in a little closer throughout an orbit that lasts tens of thousands of years. Over lengthy eons, its gravitational pull, albeit milder than that of nearby giants like Jupiter, would produce the orbital patterns that scientists were observing. The characteristic clustering seen was consistently not produced by attempts to model these alignments without an additional planet. The results of the quantum AI are remarkably consistent with these well-established hypotheses. It revealed a mass range between 5 and 10 Earth masses that matches the previous predictions and suggests a far-off area that is consistent with a long orbital period. The AI conclusion bolsters astronomers' confidence that they are headed in the right direction because it closely matches the mass-to-distance ratio that previous models anticipated. It would have raised new questions if the AI had detected a mass that was significantly larger or smaller, or indicated an orbit that was completely inconsistent with earlier estimations. Rather, it bolstered the hypothesis that planet may not inhabit exactly the kind of space described in the earlier analysis. The way that these recently discovered signals offer an environmental context for the peculiar configuration of some trans-Neptunian objects is equally significant. These orbits seamlessly link to the gravitational signature that the AI detected rather than being sporadic anomalies. Consider it similar to solving a problem. Only recently have scientists been able to hold the vital component in their hands, although it was always presumed to be there. Some experts consider this to be a near-perfect match because the AI's conclusions so closely match the theoretical design. They contend that an explanation's likelihood of being accurate increases with its simplicity. In this instance, the idea of a slow-moving planet of intermediate mass is supported by all lines of evidence: distant object groups, concealed infrared patterns, and gravitational anomalies. Astronomers still need to gather more supporting evidence, of course, but many people are excited again that Planet 9's existence is more than just a notion. 2. Opposing theories. Now that the results of quantum AI indicate a distinct huge object at the periphery, scientists are debating a single key issue. What is it exactly? According to the main hypothesis, Theory A, it is a typical planet, possibly a gas or ice giant that formed life early in the solar system and was sent into a far-off orbit by gravity. It would probably resemble Neptune more than Jupiter, with mass estimates of between 5 and 10 Earths, but probably less active in terms of atmospheric dynamics, colder and dimmer. With telescopes that use visible wavelengths, the feeble reflection of sunlight at that distance would make it appear ghostly and difficult to see. Theory B, the second possibility, is a stretch of the imagination. Perhaps it is a primordial black hole from the universe's early history rather than a planet at all. In that instance, it could have many Earth masses even though it is only a few centimeters across. Proponents of this perspective refer to anomalous infrared data that could be difficult to reconcile with a typical planet. Although a black hole doesn't generate light in the conventional sense, any nearby stuff may begin to emit weak signals as it warms up. The primordial black hole theory nevertheless piques the interest of academics who approach cosmic data from unusual perspectives, even if the majority of astronomers favor the planet scenario. They point out that black holes can resemble the gravitational pull of planets and avoid easy detection. And they suggest that the measured signals might correspond to fewer known emissions associated with small black holes. If this idea is confirmed, it would be revolutionary, bridging the gap between high-energy astrophysics and studies of the solar system in a way that no one had anticipated. Large planets and tiny black holes both challenge our conception of what is feasible in our cosmic backyard. Whichever of these proves to be accurate, the revelation is significant in and of itself. We have found a brand new member of the Sun's family buried in the shadows. If it is a typical planet, we have discovered something that changes the way matter in our solar system may have changed or been trapped over billions of years. If it is a black hole, either result forces scientists to re-examine the conventional textbook accounts. Which theory is true cannot be determined only by the quantum AI data. An object's nature can only be partially understood by detecting its tiny infrared trace and gravitational attraction. To determine the truth, more observations are needed, such as measuring a genuine atmosphere spectrum if it is a planet, or identifying strange gravitational lensing phenomena if it is a black hole. Both of these hypotheses have the ability to change our perception of what lives in the solar darkness, and they are currently the subject of intense discussions. Unexpected turns. The existence of anything large beyond Neptune was the main finding of the quantum AI, but it did not end there. A few anomalies that potentially indicate additional levels of complexity were brought to light by the algorithm as it processed the data. One of these is an apparent wobble in the object's motion, a slight variation that is neither constant nor unique, and that points to a gravitational pull. Astronomers would anticipate consistent effects from one scan to the next if it were only one planet with a simple orbit. Rather, the evidence suggests minor changes that prompt further inquiries. This wobble is interpreted by some as the pull of a ring system or the moon. Similar to how the Earth-Moon system causes modest adjustments in each other's orbits, the newly discovered object's gravity might result in slight variations in the planet's path if it has a satellite of significant mass. These periodic shifts could also be caused by passing lumps of ice, a disk of debris, smaller partner objects, or components of the planet's atmosphere. The repetitive pulsing in what seems to be the object's reflected infrared light or thermal emissions is even more perplexing. As a consistent pattern that was apparent in successive measurements, this pulse stands out. Periodic brightening can be caused by a variety of natural processes, according to scientists. Thermal vents, revolving atmospheric elements, or sunlight reflected and regulated by a ring-like structural element. However, the intervals appeared strangely constant, raising the possibility that it is more than simply random cosmic noise, which leads to crazy speculation. The controversial theory that these pulses might indicate artificial activity has been put forth by a small group of researchers. Although they emphasize that this is extremely unlikely, it is nevertheless a possibility in the absence of a convincing explanation. The pattern's association with a rotational period is a more likely hypothesis. Perhaps a ring system frequently passes in front of a faint background glow, or the planet or related objects rotate in a way that focuses infrared radiation at regular intervals. The possible discovery is made even more intriguing by these surprising details. Our understanding of the solar system's outer border would be significantly impacted if we were able to identify a planet and a crucial group of satellites orbiting it, or if it had a complex ring structure. Alternatively, the existence of a companion object of some sort alters our perspective on the origins and development of this area. Astronomers are aware that they have discovered more than just a one-note discovery, regardless of the reason behind these abnormalities. It might be the first indication of astronomy's implications for a much more comprehensive picture. The implications for astronomy and planet science are profound if more observations verify that Planet 9 is real. The discovery of such a large world so far away challenges our understanding of the evolution of our solar system from a theoretical perspective. According to current ideas, Gas and ice giants originated nearer the sun and then moved outward as a result of residual debris or gravitational interactions. But a planet in such a far-off orbit adds new details to that tale, maybe suggesting more active early movements than previously thought. According to some conjectures, the discovery of a new planet may force astronomers to reevaluate their own definitions. When Pluto was reclassified as a dwarf planet, we immediately seen a significant change. The addition of a massive far-off companion might rekindle discussions about what constitutes a planet, its size, composition, orbit, and ability to clean its surroundings. Furthermore, since black holes are not typically thought of as typical members of the solar system, if the object turned out to be a black hole after all, it would defy classification. Regardless of classification, the discovery of Planet 9 would let researchers study exoplanets that orbit other stars. In an effort to comprehend how planets arise under different circumstances, scientists frequently study far-off star systems. Similar searches around other stars may be prompted by the discovery that a star like our Sun can harbor a hidden massive planet or a black hole at great distances. We may be reevaluating the number of undiscovered companions in star systems if these distant objects are more common than previously believed. Furthermore, if it is a planet, it might be used as a planetary chemistry and physics lab. To further our knowledge of the diversity of planetary kinds in the universe, astronomers could even use remote sensing to examine its atmosphere, if it has one, or extract components of its makeup. Additionally, if it has satellites, those might be just as fascinating as some of the moons of Saturn or Jupiter. On worlds that far away, special chemical or geological processes could occur with little solar heat. The impact of this revelation may also be felt on a cultural level. Many recall the controversy that erupted outside of the realm of professional groups when Pluto was voted off of planethood. Imagine how thrilled the public would be if scientists announced the discovery of a new, uncontested big planet in the solar system. It would inspire new generations to explore music, astronomy, and spark a renewed interest in space, speculative possibilities. Even if the AI's results lend credence to the notion of a planet or even a black hole, some scientists use the occasion to propose other explanations for how an unidentified mass might have gotten so far from the Sun. The first is that Planet 9 could be a free-floating world that was previously a caught renegade planet that roamed the galaxy without a host star. It may have passed close enough to the Sun at one point in its journey for the gravity to lock it into a broad orbit. If accurate, it would indicate that Planet 9 did not develop in the typical manner orbiting our star. It only gravitationally coincidentally joined our system. According to some, it might be the remnant core of a tiny star companion that was a part of a binary system that orbited the Sun billions of years ago. In that case, a compact residue may have been left behind when the companion star disappeared or was expelled. The accurate gravitational data from the quantum AI may give this theory some credibility, but astrophysicists think it's more of a reach. The notion that we are dealing with something more exotic than a typical planet may be strengthened if the detected signals suggest an unusual density or energy signature. In either case, portions of cosmic history would be altered, requiring us to view the solar system as a location where external objects occasionally enter and remain rather than as an isolated entity. Similarly, a black hole scenario would go even beyond, connecting local celestial discoveries to remnants of the early universe's activities. Each of these possibilities leads to fresh research questions, such as whether moderately massive black holes may settle permanently around a regular star like the Sun, how prevalent rogue planets actually are, or how frequently tiny stellar remnants travel across space. These hypotheses are not widely accepted despite their popularity, primarily because the more straightforward theory that a planet originated among the others remains more likely. However, unless this buried mass's precise identification is established, one cannot dismiss such notions. Actually, the current debate demonstrates how discoveries can inspire scientists to adopt daring, non-traditional approaches. The community is invigorated by the quantum AI system's data, which is both robust and interpretable. Naturally, more focused observations will aid in reducing these options. The information needed to determine whether we are looking at a native planet, a renegade interloper, or something else entirely may be gathered by monitoring particular wavelengths, performing deep sky scans with specialist equipment, or even creating fictional probe trips, identifying the item. How accurately the quantum AI study advises astronomers to search for the concealed body is one of its most intriguing features. The approach restricted the search region to within approximately 0.3 degrees on the sky by cross, referencing minor thermal or reflection signals in the JWST data with gravitational clues in the Kyper belt. Considering the size of the outer solar system, this slice is astonishingly concentrated. This is like switching from looking at entire constellations to looking at a small region close to a certain star cluster. Observers can plan specific time on high-powered telescopes to further examine that zone because the location is so well constrained. Over the course of weeks, they might snap numerous pictures, noticing any gradual movements of dim objects against the starry background. If there is a big planet out there, it should move slowly throughout these periods. Direct detection may be more difficult if the black hole theory is right, but small changes in the cosmic background or gravitational lensing may still be indirect indicators. These, the thing worse down, many things, ways of mind orbit, but it being orbit, it ain't good. Yeah, me with limits, with that and the dians, and then, you're many almost bad, and the love bar, and made us sit in with saying it. The Burma puts, and dividing you on better than meditapai. What one being beneath fuel, or weapon pill, on wombers, what when they make a meditor, or the playing in a beauty, and then it liquor, one mixed it is, one become bizarres, over days, a mixer, or the second the, what maybe this, one maybe a bull, on many. Coordinates, along with the AI's 97.2% confidence level, provide a clear path for further investigation. The days of looking in all directions in the hopes of finding a fortuitous break are long gone. The best ground-based and orbital telescopes now have a perfect set of targets to examine. For a field that previously had trouble determining exactly where to search for Planet 9, this increased focus is a huge step forward. But there are still difficulties. The object may appear faint against the background of diffuse galactic light and distant stars, even with a crisp sky map. If it resembles a planet, it might emit weak infrared thermal radiation or reflect a little amount of sunlight. In order to differentiate a slow-moving planet from the numerous faint specks in that region of the sky, observers will need to improve their methods. Some suggest highlighting any motion with sophisticated picture reduction techniques and repeated exposures. It is impossible to exaggerate the importance of that 0.3 degree pinpoint. It implies that astronomers are no longer limited to using formulas that predict the location of Planet 9. They can instead pursue a genuine observable lead. In a comparatively short time, successful detection and tracking would either support or contradict the AI's conclusion. The best indication to date that humanity has finally caught up to a planet or black hole that has long been buried in the cosmic shadow would be if the discovered object matched the predicted brightness and velocity. It is a moment that renews our determination to push limits, transforming the previously unthinkable into a new reality that expands our horizons. Thank you for watching the video. Please like and subscribe for similar content.